Hello, everyone. In this section, we're going to talk about alternating series. This would be section 9.5 in the book that we're using. So let's begin by actually the general form. So what does the general form of alternating series looks like? I have a couple of forms here. The one on the left kind of looks like the one on the right. The difference is -1 to the n minus 1 as opposed to -1 to the n. And the effect of that -1 is to cause this series, the one on the left, to start with a positive term. Then the second term will be negative, positive, negative, and so on. And if you start the series on the right side, where n is 1, -1 to the first power is negative. So the first term, the sign on the first term will be negative. The sign on the second term will be positive, negative, positive, and so on. Both of these series are alternating series. Again, the difference is whether you start the term as positive or negative. So what are alternating series? These are infinite series, just like many other infinite series we've talked about, that contain both positive and negative terms. Positive, negative terms. Now, it is important that the signs alternate. So for instance, if I have a series that goes like this, let's say I have -2 minus 3 plus 4 minus 5 plus 6 plus 7 plus 8 minus 9 minus 10 minus 11 minus 12, and so on. This is not an alternating series. You see that? You have 2 negatives, a positive, negative, 3 positives, 4 negatives, and so on. The terms, again, must alternate. They have to, a plus followed by minus or a minus followed by the plus. So once that is in place, then let's talk about our first theorem here. So this first theorem, also known as the alternating series test or Leibniz test, goes as such. So the theorem says, suppose we have an alternating series. And again, you could start with either of the two on top. I went ahead and stayed with the one on the left side. So suppose we have alternating series that are in this form. The series is convergent if number one, the next term in the series is going to be less than or equal to the previous term in the series. So what number one implies is that if the next term is less than the term prior, then that means the series must be decreasing. Okay, and this is for all or for every, the symbol I have. This is a universal quantifier. So that means for every n. And remember, n is a set of natural numbers. We're working with series here. We defined a lot of these earlier in the lectures. Number two of the alternating series test, the limit of the nth term has to be 0. Now remember, when we talked about the divergence test, we said if the limit is 0, then that really means we should keep going, right? We cannot conclude that the series converges if the limit is 0. However, in the case of alternating series only, the limit must be 0. And of course, the added condition here is that the sequence must be a decreasing sequence. Now, how are we going to prove these? Well, the ways to prove number one, this one, the decreasing one, is to show the ratio of the next term to the term prior is less than or equal to 1. That's one way. Or the difference between the kth term and the next term after that. Or we can go a sub n minus a sub n plus 1. It doesn't matter. The difference has to be positive. If the difference is positive, it really means this in terms of numbers. So suppose I have 7 minus 5. This is my kth term. This is my k plus first term. And the difference is positive, isn't it? 2 is greater than 0. Notice 5 is less than 7. So that's our way of saying the series is decreasing. Sorry, there you go. So I made up just a couple of numbers to clarify that symbol. This is the kth term. This is k plus first term. The difference, positive. And the sequence is decreasing. Okay. The other way to do this, the decreasing business, is to show that f of x, the continuous version of the sequence, is decreasing for all x greater than or equal to 1. Again, remember, the reason we go x greater than or equal to 1, that condition, is because the set of natural numbers, remember natural numbers, start with 1, 2, 3, 4, and so forth, right? So because natural numbers begin with 1, therefore the continuous versions we always start with 1. So that way we are aligning the indexes, or the domain, if you will, I should say, not the index, but the domain. The continuous version domain, the lower portion, the lower part of the domain, and the lower part of this domain. And to show that, we use Calc 1 method, uses a first derivative test. And I'll do that during when we do the exercises. I'll show you how this is done. Okay. So now let's see. Okay, so let's continue on now. Now, what if conditions 1 and 2 are not met for the alternating series test here? Well, if the conditions aren't met, then clearly we cannot use this test, right? So the test is, what we say, is inconclusive. So you cannot conclude anything from that test. And next, I want to show you the remedial actions in a way if the assumptions fail to hold. Not assumptions again, I'm sorry. If the item 1 and 2 of the test fail to hold. So if the sequence is non-decreasing, right? If it's non-decreasing, means condition 1 fails. Then usually you can do this by testing for perhaps absolute convergence, or use other tests such as the Dershowitz test. Okay, so we could use that. Now you could read about these other tests because they're not within the scope of what we're doing here. But nonetheless, these tests do exist. So that would be one remedial action. The other one is if both of these conditions, 1 and 2, if neither of those is clear, that means I'm not sure how to find the limit, and I'm not sure how to show this series is decreasing because it may be cumbersome or complicated, then in that case, the remedial or corrective action may be to use Abel's test. Okay, so those are just a couple of suggestions or recommendations. Now, having said that, let's actually look at some example of these series and see if we can establish the convergence or divergence of those. Now, let's do for our first example here. We're going to look at an alternating series, -1 to the n, and then 1 over n. Now, from earlier work, remember sigma 1 over n, we recognize this series as 1 plus a half plus a third and so on. This is the well-known famous harmonic series, right? So we have this harmonic series, and we already established the convergence divergence of harmonic series. If you recall, harmonic series are divergent. Okay. Now, the series on the left, aside from the signs, so it looks like some kind of a harmonic in there, right? The only difference is it's going to alternate. So if I begin with n1, and what is this series going to look like? Well, -1 to the 1 is negative, so it's going to be -1, positive a half, negative a third, plus so on and so forth. So that's going to be the form of this series. And this is what we call alternating series, right? It's because the signs alternate. And the series itself, which resembles harmonic, this is called the alternate harmonic series. Alternate harmonic. Now let's talk about or establish convergence of or divergence of this one. item number one. Number one, or let me just number it. Number one, to be consistent with up here. Remember up here, we need to show decreasing, and then we show the limit is 0. So to show that this is decreasing, I can use the calculus method using first derivative test to do that. So the continuous version of the form f of x is going to be 1 over x. Now, it's important to note, by the way, in this series, the an, let me back up here. The an that is in the general form here, an is the actual function that we work with in the series. So the actual function here is the harmonic 1 over n. The negative 1 to the n, remember, that simply causes the terms to alternate in sign. So if the function is 1 over x, then the derivative f prime of x is going to be the derivative of rewriting 1 over x, and that's going to be negative 1 over x squared. And you can see that this expression is always negative because x squared is positive, so negative of a positive fraction is always negative. And therefore, we know that the function f of x, therefore, is decreasing, and that satisfies item 1. Item 2 is the limit of the nth term. So if I look at the limit now of 1 over n as n approaches infinity, clearly that's 1 over infinity, and that limit approaches 0. True? And there we have that one. So the limit is 0, and both conditions of alternating series test is satisfied, and therefore we say that the series actually converges. Therefore, although harmonic series diverge, the alternate harmonic series converge. And that has to do a lot with the fact that you're combining a bunch of positive and negative terms. And those negative terms actually cause this series to converge, not to converge to a value. All right. So this would be just an example of what we call alternating series tests or Leibniz tests. Now, the next idea in this section is this one right in here. So we're going to look at our theorem number 2. Theorem number 2 has to do with estimating the error or error estimate in approximating an alternate series. And what we mean by approximating alternating series is approximating the sum, the total. And first, I just want to clarify before you actually see the theorem here. When we talk about the accuracy of estimates, so for instance, if we require that the error, E stands for error here, absolute value of error, because error could be positive or negative. If the absolute value of that, we require it to be accurate to 1 decimal, that means the error has to be less than 0.05. 2 decimal accuracy requires absolute value of error be less than 0.005. So the number before decimal, 1, 2, 3, 4, references how many zeros we have before 5. So if we continue along this pattern, for k decimal accuracy, you do 0.5 times 10 to negative k. So if you want 5 decimal accuracy, it's 0.5 times 10 to negative 5 power. Okay. Now, let's see. So what does this error in approximation theorem 2 looks like? So here's the theorem actually now. I'm going to state the theorem that's up there. Okay. So this theorem goes like this. We're going to let sigma negative 1 to the n minus 1 a n be our alternating series. And we want this to converge. Okay. And let me erase this part. Okay. So suppose we have an alternating series, and let's let this series be a convergent alternating series. Be a convergent series. Okay. Now, if it's convergent, that means the sum exists, right? So if, like always, if we let S be the sum, if S is the sum, that's from 1 to infinity of the alternating series, the sum of this series of the series, and then the absolute value of the error, which is equal to the actual sum minus the sum based on n partial n terms, which we call the partial sum. Remember, S here is the actual total, actual sum. This is an approximation to the sum. Okay, that's going to be less than or equal to a sub n plus 1. Now, this theorem is actually very useful, very powerful, because it tells us based on selected number of terms how accurate the approximation is. Now, very few series we can do that with, right? So for example, let's say S sub 4. That means I'm using 4 terms of a series, S sub 4. If I use 4 terms of a series to approximate the sum, and the series is an alternating series, then the error in the difference between the actual sum and the sum based on 4 terms is going to be less than or equal to the value of the 5th term. Okay, the value of the 5th term. And there you have that one. So, so let's take a look at an example. For instance, we're going to look at several examples here. So, and this one, we're going to make it easy. Okay, so suppose my series is -1 to the n minus 1, and then I have n squared divided by 2n squared minus 1. Okay, this is clearly alternating. Again, every series I'm doing in this lecture is going to be alternating. So for this series, number 1, is the series decreasing? So if I look at my f of x, and f of x is going to be x squared over 2x squared minus 1. Now we can find the derivative, f prime of x. And for the derivative, we're going to square the denominator, 2x squared minus 1 squared, which makes the denominator always positive. Repeat the denominator times derivative of the numerator, which is 2x, minus the numerator times derivative of the denominator, which is 4x. I'm doing the quotient rule of derivatives here. And then let's tidy up this thing. 2x squared, so that makes it 4x cubed. That's 4x cubed, negative 2x, and then negative 4x cubed, divided by the denominator, the square of the binomial. Of course, we got a pair of opposites. Now, as you can see here, what's left over is negative 2x over the denominator, right? 2x squared minus 1 squared. Now, this fraction is always positive. True, because x is positive. Remember the domain of x here. X is greater than or equal to 1. So x is positive. When x is positive, numerator positive, denominator always positive, and you have negative in front, which makes the fraction always negative. Therefore, this is less than 0, and hence we can say that the series is decreasing, right? So this is a decreasing series. So item 1 is satisfied. Number 2 was the limit n goes to infinity of the nth term, n squared over 2n squared minus 1. And that limit, again, several ways we can show this using the theorem on horizontal asymptotes. For example, the ratio of coefficients, it has the same degree on top and the bottom. The ratio is 1/2. Or you can say This is in the form infinity over infinity, the indeterminate form of the limit, and then apply Hopital's rule. And a couple of iterations of Hopital will make this fall out to a half. Or you can divide the top, for example, by n squared. And the denominator, we go 2n squared by n squared minus 1 over n squared. Now, n squared over n squared is 1. 2n squared over n squared, and that's going to be 2, correct? So this is 2 minus this limit, 1 over n squared, goes to 0 as n goes to infinity. So you get your 1/2 that way. So however you do this, so therefore, for this one, we showed number 1 is satisfied. Item number 2, that was limit, has to be 0. This one is not satisfied, right? So for this example, again, we're going to say that, what you call it? This limit is not 0, therefore, therefore, the series diverges. Okay, that one diverges. Again, the limit of the nth term had to be 0, and it's not, although it was decreasing. So it's kind of like the harmonic, right? Harmonics, of course, are not alternating, just a straight harmonic, but the limit was 0, but the series diverged. So it's the same idea. Okay, let's take a look at, for instance, let's look at another example here. So in this next example, suppose my series now, I'm going to look at -1 to the n minus 1 over the natural log of n, ln n. For this one, if I look at the limit of the nth term as n goes to infinity, that's the limit of 1 over the natural log of n goes to infinity. And of course, natural log approaches infinity, so this is 1 over infinity over 0. So item 2 is satisfied. Is this function decreasing? Decreasing. So for that one, again, we can look at, for example, the ratio of successive terms. So if I look at, for instance, let's look at a sub n plus 1. A sub n plus 1 is going to be 1 over natural log of n plus 1. A sub n is going to be 1 over natural log of n, right? Now, if we compare these two fractions, 1 over natural log of n plus 1 and 1 over natural log of n. Now, n plus 1, the argument of natural log, is 1 more in here than it is here. Therefore, as the argument of log increases, so does the value of the log. In other words, albeit very small, but ln of n plus 1 is larger than ln of n. And in a fraction, if the denominator, as the denominator gets bigger, the whole fraction gets smaller, correct? So we can actually say that the n plus first term is less than the nth term, right? So what we have established, in fact, is that an plus 1 is less than, we can put equal to, it doesn't matter, because logically, even though they're not equal, we know they're not equal, but that logically is not wrong if you put equal, as long as it's less than. And there you go. We established item number 1. The limit was number 2. So, and both of those hold. Therefore, this series converges by alternating series test. Okay, and there you have this one. Let's take a look at another one. So for this next one, I'm gonna look at this exercise. Let's take a look at, for instance, another example here. We're gonna look at the sum of -1 to the n minus 1 over n e to -n. Okay, so let's take a look at the limit first. So if I look at the limit n to infinity of 1 over n e to negative n, we can rewrite e to negative n using the negative exponent rule, right? So it's going to be e to the n over n. And that is, of course, indeterminate form, infinity over infinity, correct? Now, if you look at the continuous version of this, that's the limit of e to the x. Instead of n, we go by x. And the reason here is so we can use Hopital. And let's say we use Hopital. And using Hopital's rule, take the derivative of the top. So that's the limit of e to the x is itself. I'm sorry, the derivative, sorry, not limit. The derivative of e to the x is itself. The derivative of x is 1 as x goes to infinity. And this limit approaches infinity, which is not 0. Therefore, series diverges. So this is a divergent series. Okay. Now, let's take a look at another example. So for this next example, I'm going to look at something that's slightly more complicated. Let's say we want to look at the sum of the natural log of n times sine of 2n minus 1 times pi over 2. And note, by the way it looks, this is not an alternating series because I don't see negative 1 to the n minus 1. However, let's write out the first few terms of this thing. So for example, when n is 1, 2, 3, 4, like that. And we're just looking at the sine function. That's the sine of 2n minus 1 over 2 times pi. Right? That's what that is. Well, n is 1. N is 1 here. So 2 times 1 is 2, minus 1 is 1. 1 times pi, pi over 2. So when n is 1, this is simply sine of pi over 2. And sine of 90 degrees is 1. When n is 2, we have 2 times 2, 4, minus 1, 3. So it becomes 3 pi over 2. So the next value is sine 3 pi over 2. And sine 3 pi over 2 is negative 1. When n is 3, that's 6 minus 1, 5, 5 pi over 2. Well, 5 pi over 2 is 3 pi over 2 plus pi, so that puts you back at 1. Sine of 5 pi over 2 is 1. And number 4, 4 times 2, 8 minus 1, that's going to be 4 times 2 is 8, 8 minus 1 is 7. 7 pi over 2 is pi plus 5 pi over 2. Puts you back at negative 1. So you kind of see how this series, if you write it, it will alternate, right? In fact, just the first few terms is going to be natural log of 1 times 1 plus natural log of 2 when n is 2 times negative 1 plus ln of 3 times 1 plus ln of 4 times negative 1. So if I write this series here, of course, ln of 1 is 0, so you start with 0. The next term is negative ln of 2, positive ln of 3, negative ln of 4, positive ln of 5, and so on. And you can see that this series clearly alternates. Okay, now based on what we see here, I'm going to replace sine 2n minus 1 pi over 2 with simply 1 minus 1, 1 minus 1, so on and so forth. Therefore, the series, I'm going to write it as negative 1 to n minus 1 times natural log of it. And again, why is it negative 1 to n minus 1 and not negative 1 to n? Because when n is 1, you get 1 minus 1, 0. Negative 1 to 0 is positive. And that was the beginning of this series. Remember, I started with 1. This was a positive 1. And it just so happened times ln of 1 became 0, but the sign starts positive. And there you have it. So this works. Now, this again helps me recognize the alternating nature of the series. Let's do the limit of the nth term. Limit n goes to infinity of natural log of n. This limit approaches infinity, which is different from 0. Therefore, the series diverges. So you see how that works? The series diverges. Now, if the series diverges, there's no need to test to see if it's decreasing. As long as it fails 1, it's going to fail the test, as long as it fails one of the 2 conditions. Now, what if, let's take a look at this example. So in this next example, I have the sum n equals 2 of -1 to the n minus 1 square root of the natural log of n over n. Okay, so the limit first. That's the easier of the 2. I like to do the limit myself personally, because if it's 0, I don't have to spend so much time on showing increasing, decreasing. That takes longer. Okay, now for this one, I can rewrite it. The limit x goes to infinity. Bring this, let's see. Actually, let's do Hopital on this one. Okay, because I see infinity over infinity here. And let's do that. So we're doing Hopital on this. The derivative of the denominator is 1. The derivative of ln of x to a half is going to be 1/2 natural log of x to -1/2, right? Times chain rule, the derivative of the inside, which is 1 over x. So this limit is therefore going to be that of x going to infinity of, well, anything by 1 is itself. So this I can rewrite as 1 over the 2 and the x go in the denominator. ln of x to -1/2, I can rewrite it as the square root of natural log of x in the denominator. And as x goes to infinity, this is 1 over infinity, which approaches 0. So the limit is 0. Therefore, now I have to do the decreasing part. So is the series, or the sequence version of the series, is it decreasing? So for that, I'm going to take the derivative. I'm going to use the first derivative test. My f of x is going to be square root of the natural log of x over x. And now we can do f prime of x. The first derivative, it's going to be a long line. So square the denominator, repeat the denominator, times the derivative of the square root of ln of x is going to be, or actually, sorry, this is going to be just x, not x squared, right? We're taking the derivative of this function, not that one. So square the denominator, repeat the denominator. That looks right now. And then times the derivative of a square root of ln of x, which is going to be 1 over 2 ln of x to -1/2, right? Because the square root of ln of x is ln of x to 1/2. Using the power rule of derivatives, bring a half in front, ln of x to -1/2. And then the chain rule, the derivative of the inside, the derivative of ln of x is 1 over x minus the numerator, which is ln x to 1/2. That's instead of radical, I wrote it as that, times derivative of the denominator, which is 1. Okay, now let's tidy up this work. See what can we do here. X and 1 over x, that's good, that goes away. I see ln of x to -1/2, so I can multiply the top and the bottom of this fraction by ln of x to 1/2, so that ln of x times ln of x to negative 1/2 becomes ln of x to 0, and that's just 1. And that gets rid of negative exponent. And when we do that, what are we going to get? We're going to get 1/2 minus square root of ln of x times square root of ln of x is just ln of x, right? So this is going to be ln of x over x squared square root of ln of x. Again, that's just ln of x to 1/2. Now let's multiply top bottom by 2. Could have done it in one step, like up here, multiply by 2 top, 2 bottom also, but that's okay. Do it in this step. 2 times 1/2 is 1 minus 2 natural log of x over the denominator, 2x squared root ln of x. Now, the denominator is clearly positive. True? That's a positive denominator, right? This is positive because x is positive. And by same token, natural log of x is going to be positive. 2 times that will be positive. And negative 2 times that is definitely going to be more negative than when you add 1. It stays negative. So this one is decreasing, less than 0. Which means a sub n is decreasing. That means the nth term is getting smaller and smaller. And there you go. So it met the first condition. The limit was 0, decreasing. Therefore, by alternating series test, the series converges. And there you have that one. Okay. Now, let me actually do an example with the errors. Okay, it's because we haven't done the error. We want to do error estimate in approximating and alternating series. So for that one, I'm going to take a look at, for instance, let's take a look at this series. There you go. So in this series, the series is sigma, a -1 to the n minus 1 divided by n natural log of n. Okay, now n goes from 2. Let's make it go from 2 to infinity, not 1. They usually go from 1, but here we want to be different. Okay, now remember that the absolute value between the sum and sum based on n partial sums is going to be less than or equal to the next term, which is a sub n plus 1. Okay, and suppose the question is this: we want to estimate the sum using let's go 3 decimal accuracy, using 3 decimal accuracy. In other words, accurate to 3 decimals. Now remember, 3 decimal accuracy, that means 0.3 zeros and a 5. That's 3 decimal accuracy. So what is the next term going to look like? The next term in here. And let's say instead of estimating this sum, which we could, instead of estimating it, we want to know how many terms. So let me change that. We could estimate the sum also, but you see why I don't really want to estimate the sum using 3 decimal accuracy in a moment. Let's say I'm going to paraphrase this. How many terms are required in order to meet 3 decimal accuracy here, 0.005. So for that one, remember, we want our next term in the series, that's a sub k plus 1 or n plus 1, is going to be what? It's going to be n plus 1 and then natural log of n plus 1, right? This is the next term in the series. And let me actually stay with the notation. This is a sub n plus 1. All right. Now, we want this to be less than or equal to 0.0005. This is the error, and that is the error term, if you will. Now, at this point, I don't really know how to solve this even. So I'm just going to say by trial and error, or guess and check. By trial and error, we're going to see that n is going to be 342. And that is why I changed my mind. I don't want to estimate the sum. That means I have to add 342 terms in the series, starting with 2, 3, 4, 5, 342 terms. So I'm going to have, again, it's going to go all the way from 2 to 343 in a sub 343, because I'm starting at 2. A lot of terms, and I don't want to do that. So let's scrap this one. But again, notice that's interesting. I know how many terms I need to add in the series. Okay. Now, let's actually do this one. For this one, this next example, suppose I want to estimate the error now. And we'll look at the number of terms necessary in just a moment. So here is my next example. Okay, so in this example, I have the series. And we want, again, let's see how many terms we need. How many terms needed to approximate the sum. Let's say with this one, 2 decimal accuracies, the sum accurate to 2 decimal. So we don't need so many terms in this one. So let's see, the next term in the series, a sub n plus 1, is going to be what? That's when n becomes n plus 1. So it's going to be n plus 2 over 2 to the n plus 1. We want this to be less than or equal 0.005. And again, by trial and error, I tried different numbers for this one. And I got n to be 11. Okay, so that means I need 11 terms. Therefore, the sum is going to be approximately, S is this actual sum of the infinite series. That's what S is. This sum is going to be approximately equal to, let's see, it's going to be, I'm going to plug in the numbers. So when n is 1, you get 2 over 2, which is 1. 1 minus 1, 0. Negative 1 to 0 is 1, and 2 over 2 is 1. It's going to be 1. And the next term, because it's alternating, is going to be negative. And then n is 2. When n is 2, 2 plus 1 is 3. 2 squared is 4. So it's going to be 3 over 2 squared. 2 squared. The next term is going to be positive. Then it's going to be 4, 2 cubed. Negative, so on and so forth, plus 12, 2 to the 11. Remember, n is 11. And there you go. So if I add all these terms, and I did, I got this to be approximately 0.56. And there you go. So that's going to be the sum. And the sum is accurate to 2 decimals, means the error between the actual sum and this sum is less than 0.005. Notice, by the way, it doesn't take for this series too many terms to achieve that accuracy, and that's fairly decent accuracy, right? All right, and there you go. I think this is probably good enough. I just wanted to again clarify some things on how to use alternating series here. And that will conclude this lecture for what we wanted to do. Thank you for watching, everyone, and enjoy the video.